All right. So what we talked about first, okay, is the atomic structure. Okay, so let's say those are neutrons. Okay, neutrons have a neutral charge. Say red is going to be a proton. Okay, and a proton is going to have a positive charge. And the gray dots on the outside, okay, that's going to be an electron. Can't use a lowercase e because that'll be something later. Well, it's going to have a negative charge. Okay. Now, within an atom, you can lose electrons. However, you cannot lose a proton. If something has less protons, then it's going to be a completely different element, okay, in itself. Okay, so right now, this atom, if we look at it, has 3 neutrons, okay, with a neutral charge, 3 protons with a positive charge, and 3 electrons with a negative charge. Okay, so technically this is a neutral atom. If, for some reason, okay, this atom loses this electron, now it is positively charged. Okay, because there are 3 positive charges and there are only 2 negative charges. Okay, now let's say that this atom gains another electron. Now this atom is negatively charged. Okay, there are 4 negatively charged electrons and there are only 3 positively charged protons. Does that make sense? All right. So that's how things are going to charge. It's going to be an exchange of electrons between atoms, surfaces, objects, particles, whatever we are talking about. Okay, so let's talk about the 2 different types of charges. Let's go with yellow. Oh no, I do not like that. Green. Let's look at what a positive charge is. I just kind of mentioned it. So a positive charge, okay, that is going to be an excess of protons. Okay. Now, what also you could say is a shortage of electrons. Okay. Now, let's look at a negative charge. Negative charge will equal an excess of electrons. For negative charge, I'm not going to write a shortage of protons because, as I said, you can't really lose protons. Okay. However, if you have a positive charge, you have an excess amount of protons in comparison to the electrons. The other way you can think of it is simply that that object has lost, okay, electrons. And a negative charge, simply that object has gained more electrons than it has protons. Okay, so those are the 2 types of charges we have. Now, there's a couple ways in which we charge objects. Okay, charging objects. Okay, the first one, it's pretty simple, is charging due to friction. Hopefully everybody knows what friction is. Charging due to friction, some examples that you guys should be familiar with is if you take a balloon, which those of you who have my class, if you take the balloon and rub it really fast against your hair, okay, you will charge both your hair and the balloon. Okay, there will be an exchange of electrons between those 2. And then your hair is going to stick up and be attracted to the balloon. Guys in Diego's classes, hopefully you guys had a chance to find a balloon at home. Okay, kind of the same idea works with when you rub your feet on carpet, or rub your socks, okay, on carpet really fast. Another example would be your dryer. Okay, if you don't throw a dryer sheet in, sometimes your clothes come out really staticky. Okay, again, those clothes are rubbing around in the dryer, okay, charging each other. Okay, and then become static. You kind of can feel how parts of the shirt kind of almost stick together. So that is charging objects by friction. Second one, conduction. That's simply charging by a touch. Okay. And the third one is induction. Okay. I'll put and polarization. All right. So induction is charging by moving a charged object near a neutral object. So let's try to do this. So we have, that's too light. So we have copper wires. We have a copper wire there. Okay. On the copper wire, we have too big. We have 1, 2, 3, 4, 5, 6 electrons. Okay. And we also are going to have 1, 2, 3, 4, 5, 6 protons. I will try to positive P and negative electron. Okay. So let's say there is a negatively charged. There's a negatively charged rod. Okay. It's a negative charge. That goes near it, but notice that they are not touching. Okay. What a negative charge is going to do is going to pull the opposite charge towards it. Now, I did not go through that yet. Wow, I forgot to go that first part. Anyways, so I'll talk about that in a second. So it's going to pull light charges near it. Okay, here's our second copper wire. So we're going to do a little before and after. Okay, so the same negatively charged rod is near it. So what's going to happen after is it's going to take those negative charges and move it away. 6. Okay. Oops. And then it's going to track the 6 protons near the negatively charged item. Okay. So what you should be able to see here will be before and after. Okay. So what you can see here is that before, the copper wire is neutrally charged, right? There are 6 protons and there are 6 electrons, okay, balancing out to a neutral charge. When you bring a negatively charged object near, okay, that copper wire that's neutral, okay, it's going to separate the charges in the after picture here. You can see them separated. If I were to cut the wire right here, okay, then I would have a wire that's completely positively charged, which is down here. Okay, and I would also have a second separate wire that's completely negatively charged here. Okay, but as a wire, as a whole wire, okay, the wire is still a neutral charge because there's still an even amount of electrons and protons on the wire. They are simply rearranged along the copper wire. Alrighty? Okay, so that's charging by induction. Now, when you have the copper wire as such, where the charges are distributed to opposite ends, okay, that's called polarization. Okay, this idea of polarizing an object, okay, which you can charge it, okay, while leaving it neutral, okay, is this idea of induction, okay, and creating polarization within an object. Now let me touch back on something called the law of charges, and I apologize for not touching on this earlier. Okay, law of charges, it's very simple. A lot of you guys are familiar with it. Okay, law of charges pretty much is going to say like charges So examples of like charges are positive and a positive, or a negative charge and a negative charge. Like charges will repel each other. And then finally, opposite charges. And the only opposite charge combination you can have is a positive and a negative will attract each other. Okay, so law of charges, like charges are going to repel each other and opposite charges are going to attract. So let's go back to this idea of polarization. Here you have a negative charged silver rod, okay, come near a copper wire that is neutral. The negative charge is going to repel the negative charge away. You can see that's why these, okay, are moving away from this negative charge. Okay, so those two are going to repel each other. However, opposite charges, so again these red are our protons and they're positive, okay, are going to attract to this negative, and that's why they get pulled here. Okay, so that's the law of charges working there a little bit as well. So like charges are going to attract each other, opposite charges are going to, like charges are going to repel each other, and opposite charges are going to attract each other. Okay, so far we've talked about the atom, positive charge, negative charge, 3 different ways to charge an object, law of charges. Okay, then we're going to go to conservation of charges. Okay, conservation of charges states that the net charge in a closed / isolated, closed or isolated are synonymous, isolated system will remain the same. Okay, so again, conservation, I mean, what you have before is what you're going to have after. In a closed or isolated system, that is very key there. So if you look at the universe, okay, the universe is going to have the same charge, okay, for the rest of eternity. The net charge of the universe will never change. Okay, now you can create a charge. However, there's a little asterisk by there. Okay, you can create a charge. The key with that, if you create a positive charge, there has to have been a negative charge created as well. And vice versa. I don't even know how to spell that. Anyways, disregard the spelling. Okay, so the idea is that there are ways in which you can create a positive / negative charge. Okay, that's higher level chemistry. Honestly, it's kind of beyond me. But the rule states that if there is a positive or if there is a negative charge created, okay, that the opposite charge also has to be created at the same time. Okay, again, that's going to balance out the universe. The net charge in the universe is still going to remain the same, or in that system is still going to remain the same, okay, as long as they are balanced between positive and negative, okay? Next thing, conservation of charge. Next law. I'm going to go to a new page here. We'll go orange. We'll go Coulomb's law. So Coulomb's law essentially kind of reiterates the fact that like charges repel, opposites attract. Okay, and that the force in which they either repel or attract each other, okay, is proportional to the charges of those, okay, and inversely related to the square of the radius, okay? So the equation that we get is the electrostatic force will equal K, and I'll get to K in a second, Q1, Q2, divided by R squared. So let's look at this equation real quick. Okay, K, Q1, and Q2 are all going to have the same effect, okay, on the electrostatic force. Actually, K is a constant. That number is never going to change. Okay, therefore, if we were to double the charge of one object, we are going to double the force. Or I should say, double the charge of one of the objects. Yes, you're going to double the electrostatic force between those two charges. Okay? If you cut one of the charges in half, okay, then you will cut the force between those charges in half as well. Now, the radius, okay, is on the bottom half of this fraction. Therefore, it's going to have an inverse relationship. If the distance increases, if those charges get further apart, the force is going to decrease dramatically. Because radius is squared, okay, it's going to have a greater effect, okay, on force than the amount of charge. Okay, the further they get, okay, the much more decrease you will observe in the force. Now, vice versa, if they get closer, okay, that force is going to dramatically increase as well. Okay, so if the radius decreases, the force is going to get much stronger. So let's go through what each of these guys mean. K is our constant. Okay, and our constant's technically 8.999 or something like that, but we're just going to use, for the sake of simplicity, 9.0 times 10 to the 9th power. Okay? That's going to be K, our constant. Q is going to be our charge. Okay? Q is our charge, and I want to state that a coulomb is going to be the unit for charge. And then radius is the distance between charges, or the center of charges. Okay, so those are our pieces of the puzzle there. Other things, so I'm going to go draw this in pink real quick. So you have force equals K divided by R squared. Okay, K is positive and R and distance will also be positive. So let's say we have a scenario in which we have like charges, whether that is positive and positive or negative and negative. Okay, the force is going to be a positive number, right? Okay, because if we have two positives being multiplied together, they're obviously going to be a positive. But if we have two negatives multiplied by each other, that's also going to be a positive number. Okay, therefore the force is positive. Okay, and if the force is positive, we then said they are like charges, and that's going to indicate a repulsion. They're going to repel. Okay, they're repelling each other, a repulsion. Okay, if F, this will go back in pink. So let's look back at the equation. So F equals K divided by R squared. If both charges are opposite, then the force has to be negative. Right? Because the positive times the negative is going to be a negative, and that's going to indicate attraction. Okay, pretty simple so far. So far, so good. Next, let's like this purple. I like that color. Talk about this elementary charge. Okay, the elementary charge is the smallest isolated charge. Sorry if I zoom in and it bothers you. I just have better handwriting when I zoom in. So the elementary charge is going to be the smallest isolated charge. The smallest isolated charge we have found is a single proton or electron. And they actually have the same exact charge, a single proton and a single electron they do. Okay? They both have a charge of 1.6 times 10 to the negative 19th coulombs. Okay? Very, very small number. Now, notice I put positive / minus. Okay? Positive refers to a proton and negative refers to an electron. Again, they have the same charge. Simply one is positive and one is negative. Okay? For my AP guys, we talked about quarks, right? Quarks are what make up protons and neutrons, and technically they have a smaller charge than a proton or electron. And remember, we kind of talked about charges, or the quarks, okay, have never been isolated in nature, or at least we haven't yet. Okay, so they have not been isolated, which means the smallest isolated charge, okay, is a single proton or a single electron, and that number is 1.6 times 10 to the negative 19th coulomb. Okay, positive or minus depending if it's proton or electron. So, what is a coulomb? Coulomb, or C, is the unit for charge. Okay. Other units you should also be familiar with is meter for distance, kilogram for mass, Newton for force, meter per second for velocity, meter per second squared for acceleration. Okay, so coulomb, represented by C, is the unit for charge. Last thing before I forget, the symbol for elementary charge is going to be a lowercase e. Okay, I mentioned that earlier, that's why I didn't write E for an electron. Lowercase e, and sometimes you'll see Q with a subscript E. The subscript E there. Okay? That indicates it's the elementary charge. Again, Q means charge. We kind of covered that right here. Q is going to be charge, and there's that Coulomb unit again. Okay, or QE. Those are going to be the two symbols for the elementary charge. Coulomb, which is a capital C, is the unit for charge. what you're also going to see a lot is this idea of a nanocoulomb. Okay? In the example problem I've done with most classes, okay, we looked at the force between two balloons with a charge of positive 1 coulomb and negative 1 coulomb. And the force between those, even if they're a whole meter apart, is like 14 trillion newtons of force. An incredible amount. Okay, so coulombs are a very, very large amount. Like 1 coulomb is an extreme large amount of charge on an object. A lot of times, they'll measure it in nanocoulombs, which you'll see as lowercase n, capital C. That is a nanocoulomb. Okay, and another way to see a nanocoulomb, anytime you see this, you could think times 10 to the minus 9. So let's do a quick example. If we have 7 nanocoulombs, okay, that is 7, which would be the 9th place, okay, and that is coulomb, okay? So that's just what some of the units that you may see for measuring coulombs. June 4th, prom. Okay. So that is some of the units that you'll see. Let's see what else I want to go through. Good. I'm just trying to double check that I've covered everything. The last thing, specifically for my AP kids, hey, it would be beneficial for everybody to listen to, but I don't think that you guys are necessarily going to have to do this type of work on your test. Okay, so in order to find the charge, okay, the charge of an object, well, it obviously depends on how many excess protons or electrons they have, correct? Okay, so the charge is going to equal the number of those excess protons or electrons, right? So if it has, obviously an object has 100 more protons than it does electrons, it's a positive charge. Well, how much charge does it have then? Well, if each proton or each excess proton carries a charge of 1.6 times 10 to the negative 19th, also known as the elementary charge, then it's simply the number, okay, of protons and or electrons multiplied by the elementary charge, which is the charge that each one carries. So again, Q is going to be the total charge. Okay, N, in this case, I'm going to refer to the excess protons or electrons. Okay, that's excess. Again, the N, the number, is not going to tell you the total amount of protons or the total amount of electrons on an object. It's only going to tell you the excess number, okay, which will in turn, okay, create a certain amount of charge on an object. Again, that's the only way that an object can be charged. If they have the same amount, okay, then it is a neutral charge. E is going to be the elementary charge. All right. Now, again, this is a pretty simple equation, so you can manipulate it either way to get other information. So if you take the charge divided by the number of particles, that should give you the elementary charge, which is a constant, okay? And then if you take the charge and you divide it by the the elementary charge, okay, it'll give you the number of excess protons or electrons. The two that you're really going to need to use are these two. The middle one, you obviously know what the elementary charge is. I doubt that it has you check to see if that's plausible. Okay, the only time you should use the middle equation is if the AP exam asks you if that charge is possible, right? So if you take a certain charge and it tells you the number of excess protons or electrons there are, and it does not equal, okay, the elementary charge, that means that charge is not correct. Okay. So I went through that. Good. In order to stay away from having two or one really, really, really long kind of lecture and note for you guys to go through. I'm going to cut this off here. But what I'm going to do is I'm going to go through 2 or 3 practice problems that we've kind of seen in class and try to talk my way through those. Okay? So that's kind of it, everything we've talked about. If I missed something, please let me know. I don't think I did. I'm going to also post this note itself for you guys to kind of look through, but I thought that the voiceover would be beneficial. Okay? So